James Webb Space Telescope is identifying objects in the dark ages that by best measurements we have are large, fully developed galaxies. So who ordered that? NASA's $10 billion James Webb Space Telescope has now been in space for a little more than 2 years, but the stunning results it's already returned are proving it's worth every penny. Historically, our grandest views of deep space came from the Hubble Space Telescope, but as of July 2022, James Webb takes us beyond what anything else has seen. From the faintest galaxies to the richest clusters, to mostly empty cosmic voids, to the deepest depths of far-off space, and much, much more. The Superior telescope has revealed details we've never seen before, beyond all expectations. When James Webb focused on large regions of space that appeared blank to Hubble's eyes, it detected something mind-boggling. 900 trillion stars have mysteriously vanished into the void of space, and things are getting scarier by the minute. What happened? Where did the stars go? How did they utterly go without a trace? Join us as we dig deeper into the shocking discovery made by James Webb and how the disappearance of that many stars might affect our planet and our very future. First of all, you have to know that James Webb outperformed Hubble by more than we expected. When you look at the capabilities of James Webb and Hubble side by side, you would expect that our newest space telescope could do much more in less time. Whereas Hubble has a primary mirror that's 2.4 meters across, Webb's segmented mirror spans 6.5 meters. This leads to a resolution that's 270% as sharp for the same wavelength light and light gathering power that's 730% as great as Hubble's. From the physics of optics alone, that's how much better and faster James Webb should be than Hubble, not including the advantages James Webb also possesses in terms of cooling, wavelength coverage, and instrumentation. In other words, for the same amount of observing time, you'd expect that James Webb would collect 730% as much light as Hubble. But James Webb, as you can see in the comparison of its composite image of galaxy clusters SMACS as A723 with that of Hubble, is doing even better than that. Hubble time is divided up into orbits as, from its position in low Earth orbit, it completes a revolution around our planet every 96 minutes. A total of 6 orbits, 4 in optical wavelengths and 2 in infrared wavelengths were used to make the Hubble composite. You'd expect, based on simple math, that 6 orbits multiplied by 96 minutes per orbit would equal 96 hours or 576 minutes of Hubble time, but there's only a total of 4 hours or 203 minutes of Hubble data that's gone into these images, despite nearly 3 times as much of Hubble's time having been devoted to this target. For comparison, James Webb observed this target for 12.5 hours and got 12.5 hours worth of data. What's the difference? Location. Hubble, because it's in orbit around Earth, spends more than 50% of its time with the Earth and the Earth's atmosphere in the way of its desired target, and can only acquire useful data when its target is in full, unobstructed view of the telescope. Meanwhile, James Webb is some 15 million kilometers away at the L2 Lagrange point. It always faces away from the Sun, away from the Earth, and away from the Moon. It never has to contend with these obstacles to pristine observing, and so its observations of targets are 100% time efficient, as opposed to less than 50% time efficient like Hubble was. This improved efficiency extends to all observations taken with James Webb and should enable faster, better science than Hubble could ever achieve. In other words, James Webb gave us the proof we needed. Not only can James Webb find the objects that appeared blank to Hubble's eyes, in many cases it can resolve them and examine their properties, whereas Hubble could not even see them at all. This helps us achieve one of James Webb's main science goals, to teach us, in the greatest details possible, how the universe around us grew up and came to be the way it is today. For instance, nearby Jupiter appears as never before. Its bands, rings, aurorae, and moons appear alongside background galaxies. James Webb viewed exoplanets directly with infrared imaging. Spectroscopically, transits detect absorbed light and transmitted light, revealing molecular presences. Star-forming nebulae display unprecedented details from new young blue stars to gaseous features. James Webb showcases what Hubble cannot. Meanwhile, Webb's initial alignment image grew spectacularly. Now a 140-plus megapixel view, it expansively reveals far-flung galaxies. Just 1% of this view contains 1 to 100 identifiable objects. Massive, evolved, complex galactic shapes appear at all observed distances. Additionally, disk galaxy candidates surprisingly appeared at extremely early times. James Webb also viewed the most distant star ever, Earendel, but arguably its greatest images are of individual galaxies. Webb's views reveal gas, dust, stars, and more. Central black hole containing cores. Shine in mid-infrared light. Star-forming gas bridges appear between interacting galaxies. From Hubble to James Webb's near-infrared eyes to the eerie, unfamiliar mid-infrared views, the universe is coming into focus as never before under Webb's watchful eyes. But in a shocking observation, James Webb has detected trillions of stars disappearing without a trace. But how? Where did they go? The two leading theories about what happened are that either they're still there, still erupting its way through its death, throws with less luminosity and perhaps obscured by dust, or it just up and collapsed into a black hole without going through a supernova stage. But in the worst-case scenario, the universe is just disappearing, and we're powerless to stop it. It's been nearly a century since scientists first theorized that the universe is expanding, and that the farther away a galaxy is from us, the faster it appears to recede. This isn't because galaxies are physically moving away from us, but rather because the universe is full of gravitationally bound objects, and the fabric of space that those objects reside in is expanding. But this picture, which held sway from the 1920s onward, has been recently revised. It's been only 20 years since we first realized that this expansion was speeding up, and that as time goes on, individual galaxies will appear to recede away from us faster and faster. In time, they'll become unreachable, even if we journey toward them at the speed of light. When you look out at a star whose light arrives after traveling toward you for 100 years, you're seeing a star that's 100 light years away due to the fact that the speed of light is finite. But when you look out at a galaxy whose light arrives after traveling toward you for a journey of 100 million years, you're not looking at a galaxy that's 100 million light years distant. Rather, you're seeing a galaxy that's significantly farther away than that. The reason for this is that, on the largest scales, objects that aren't gravitationally bound together into galaxies, groups, or clusters, the universe is expanding. The longer it takes a photon to travel from a distant galaxy to your eyes, the greater the role of the universe's expansion, implying that the most distant galaxies are even farther away than the amount of time the light from them has been traveling. This shows up as a cosmic redshift since light is emitted with a particular energy and hence a particular wavelength. We fully expect that it will arrive at its destination with a particular wavelength as well. If the fabric of the universe were neither expanding nor contracting, but rather were constant, that wavelength would be the same. But if the universe is expanding, the fabric of that space is stretching, as shown in the video above, and hence the wavelength of that light becomes longer. The great redshifts we've observed for the most distant galaxies have absolutely verified this picture. But we can do much more than determine that the universe has expanded and continues to expand. We can use all the information we gather to conclude how the universe has expanded over its history, which in turn tells us what the universe is composed of. Once the light leaves a distant cosmic source, the expanding universe stretches the wavelength of that light. This leads to a redshift where the more distant objects will have their light redshift for longer amounts of time, when different components of the universe were more important. By measuring sources at a whole slew of distances, discovering their redshift, and then either measuring their intrinsic versus apparent size or their intrinsic versus apparent brightness, we can reconstruct the entire expansion history of the universe. In addition, since the way the universe expands is determined by the various types of matter and energy present within it, we can learn what our universe is made out of: 68% dark energy, equivalent to a cosmological constant, 27% dark matter, 49% normal protons, neutrons, and electrons matter, 0.1% neutrinos and antineutrinos, about 0.8% photons, and absolutely nothing else, including no curvature, no cosmic strings, no domain walls, no cosmic textures, etc. Once we know the components of the universe to this degree of precision, we can simply apply this to the laws of gravity given by Einstein's general relativity and determine the future fate of our universe. What we discovered when we first applied this to the discovery of a dark energy-dominated universe was shocking. First off, it meant that all the galaxies that weren't already gravitationally bound to us would eventually disappear from view. They would speed away from us at an ever-increasing rate as the universe continued to expand and expand and expand, unchecked by gravitation or any other force. As time went on, it meant that every individual galaxy group or cluster would be surrounded by an ever-expanding region of space that became more and more barren and practically empty. When you look at the Hubble ultra-deep field, for instance, Every single galaxy within it would eventually disappear, except for the Milky Way and Andromeda. So, as we wait and see what else James Webb will uncover, let's remember that we're in an era of unprecedented astronomical discovery, and these findings may very well shape the future of our understanding of the universe.